All right, AP Chemistry. This is your video lecture that is going to finish up Chapter 2. We're only going to cover one section in this video lecture. I wanted to dedicate an entire video for this one section because it is going to be so instrumental in the rest of this course, being able to name simple compounds. What I want you to get at, name type 1 binary compounds, name type 2 binary compounds, name type 3 binary compounds, and name acids. Pretty simple. Be able to name the stuff we're talking about. So let's get into it. We're naming compounds. Let's start with what a binary compound is, since that's all over what the objectives say. A binary compound is simply composed of two elements. Binary, two things, two different elements. They can be ionic or covalent, doesn't matter. The two different types that we're going to look at, binary ionic compounds, which is a metal and a non-metal, right? Both of those things are going to ionize. They're going to have opposite charges, and then they're going to attract their ionic compound. We can also have a binary covalent compound. Here, it's not going to be an ionic, and obviously not an ionic bond, but not an electrostatic attraction. It's going to be a sharing of valence electrons, so it's going to be a non-metal with a non-metal. So let's look at binary ionic compounds, aka type 1. The cation, that's the positive one, is always named first, and the negative, the anion, is always second. A monatomic cation takes its name from the name of the parent element. A monatomic anion is named by taking the root of the element name and adding IDE at the end. So, examples. We got KCl, that's a potassium, that's the first element, it's the metal. Then the second element is chlorine, but I'm going to drop the last syllable and replace that with an IDE, so that's potassium chloride. And I have magnesium bromide, and then I have calcium oxide. It's really important to notice here that the ionic charges are equal and opposite. Equal and opposite meaning they're balanced. Potassium and chloride both forming one charges, positive one and negative charge, or positive one and negative one. Magnesium forms a +2 charge. Each of those bromides form a negative 1. There are two of them, so that's a total of -2. So that balances out the +2. And then the calcium ion forms a +2. And the oxide ion forms a -2. So they are balancing out. That's how we know how many of each ion has to be present. What does it take in order for the overall charge to be 0? Moving on to type 2. We're still talking about binary ionic compounds, but very specifically, the metal in this binary ionic compound is going to be one of those metals that forms more than one type of positive ion, meaning sometimes it's a +1, sometimes it's a +2, maybe sometimes it's a +3, maybe sometimes it's a +4, but it's forming more than one charge. Now, we're not saying that when you're dealing with this atom, it's going to ionize, form a +2, and then all of a sudden it'll become a +3. That's not what we're saying. We're saying there are different charges on different types of iron, for example. And because of that, we have to somehow communicate to the reader what that charge is. With the main group metals that we were talking about with group 1 binary ionic compounds, they always form the same charge, right? Magnesium always forms a +2. Potassium always forms a +1. But iron, for example, forms a +2 or a +3 charge. I have to tell you which one it is when I'm talking about it. To do that, I'm going to use a Roman numeral. That Roman numeral is going to indicate the charge of the metal cation. Most of these metals that form multiple charges are called transition metals. And so whenever you're making a compound that uses a transition metal, be sure that you're probably going to need to include a Roman numeral. And but that doesn't mean all transition metals. There are a couple transition metals that they truly are transition metals, but they just happen to only form one charge. Like zinc, for example, only forms a +2 charge. You don't have to include a Roman numeral. The Roman numeral is designed to tell you what charge you're dealing with if there's multiple charges. For any element that only forms one charge, you don't have to. So some examples of this, copper bromide. Copper forms a +1 or a +2 charge. So how am I going to know which one it is? And again, that's going to be important so I can know how many bromides I need to put on this compound. Well, I say copper 1 bromide. So that means that this copper is a +1. That means in order to balance that out, I only need 1 bromide. So I know that's CuBr. We've got iron 2 sulfide. It tells me that this iron is a +2 charge. So since sulfide is always the -2, I just need one of them to balance out. And then we have lead 4 oxide. The type of lead has a +4 charge. That means I'm going to need 2 oxides in order to balance it out. We're going to talk about polyatomic ions very, very quickly. On page 66 of your textbook, I know that's what you guys have now, there is a table 2.5, I believe. Make sure you memorize all of the ions on that sheet. You will be having, you may already have one, a polyatomic ion sheet, and you will have access to that for most of your assessments, but it's going to be a lot easier on you in the long run if you get used to some of those more common polyatomic ions. When we name ionic compounds with polyatomic ions, we simply use the name of that polyatomic ion as though it was the name of an element. So NaOH, sodium hydroxide. Okay. Next one here, that is a nitrate polyatomic ion. It's the anion, so I put that at the end. It's just the name of the polyatomic ion. Magnesium nitrate. All right, I know that I need 2 nitrates because I know that nitrate is a -1. Magnesium is a +2, so I need 2 nitrates. Then we have ammonium sulfate. Okay, in this example, we actually have 2 different polyatomic ions. I don't have to include any sort of Roman numerals. I don't have to tell you how many of each I have because we know that ammonium forms a +1 charge and sulfate has a -2 charge, and so you're going to need 2 ammoniums for every sulfate.
To work out the formula of an ionic compound, we first select a cation and an anion. Some possible cations are shown here in blue, and some possible anions are shown here in red. Note that the anion might be an oxoanion or other polyatomic anion. Suppose we choose the sodium ion with a +1 ionic charge as the cation and a phosphate ion with a -3 ionic charge as the anion. What is the correct empirical formula for sodium phosphate? Now we can select the number of cations and anions we want to use to build the simplest formula for sodium phosphate. If we select 1 cation and 1 anion, we note that the sum of the charges is -2, so the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add another sodium ion so that there are 2 cations and 1 anion, we note that the sum of the charges is -1. Therefore, the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add 1 more sodium ion for a total of 3 sodium ions, we obtain charge balance and a correct empirical formula for sodium phosphate.
Thanks, robot lady. All right, we'll move on to type 3 compounds. These are binary covalent bonds. And by the way, there aren't going to be any questions that say like, hey, what's a type 3? What's a type 3 compound? What's a type 1 compound? That's not the point of naming this as type 3. Just trying to give you some sort of scheme to work off of here until you get used to the concept here. Binary covalent. Because it's covalent, you have 2 different non-metals. When you see a covalent bond or it says a molecular bond, something like that, you're talking about non-metals here for the most part. First off, the first element in the formula is named first, using the full element name. Okay, the first one. The second element is named as if it were an ion, or as if it were an anion. Now, it's not an anion because we're not forming ions here. Think about it. If they were anions, you'd have 2 negative charges. They wouldn't attract. You wouldn't have a compound. These are not ions. You're simply satisfying 2 different valence shells here. That's why these 2 things are getting together. So the second element is named as if it were an anion. I mean with the IED, that is. Prefixes are used to denote the number of atoms, because again, this isn't an ionic compound where you know that the charges have to balance. So you just juggle how many of each ion you need until those charges balance, because there aren't any charges here. There are no charges to balance, and so I can't just memorize what charges these things are going to form. It's not going to help me here. So I have to tell you as the reader how many there are. For example, the prefix. The prefix mono means one. Actually, I should go that. If I say di, I mean two. If I say tri, that's three. Tetra is 4. Penta is 5. Hexa is 6. Hepta is 7. Octa is 8. Nona is 9, and deca is 10. That actually continues to go on for quite a ways, but we aren't going to get that high. If you ever get into some hardcore organic chemistry, they'll actually have you go a little bit further than that, but for our purposes, we'll probably only need those first 10. Now, you're always going to tell the reader how many of that atom is there, that element is there, unless it's on the first element. There's only one of the first element. One thing I didn't mention here, the first two things here, I was saying, the first element and then the second element. How do I know which one I say first? Whichever one is more metallic, okay, whichever has the smaller electronegativity, the one that, relative to the two atoms being bonded here is relatively more metallic, relatively less electronegative, that's the one that you list first. All right, so here's that table. This table is also in your textbook. These are prefixes that simply need to be memorized. The only things that might get a little bit tricky for you, probably 4, 6, and 7. It's probably the only ones you're going to have trouble with. Most of these are actually pretty self-explanatory. So let's look at some examples of the type 3, the primary binary covalent compounds. We got CO2. Again, there's only one of the first element, so I'm not going to say mono. And that's the only time I'm not going to put a prefix on here. So I'm going to say carbon. And I have to tell you that there are 2 oxides. So carbon dioxide. Here again, there's only 1 sulfur, but there are 6 fluorides. I'm not going to say the mono. I'm going to say sulfur hexafluoride. Here I have 2 nitrogens and 4 oxides. So I'm going to say dinitrogen tetroxide. Now you might be sitting there, well, isn't it tetraoxide? Well, yes. Typically we drop the A when you're one of those vowels if the anion begins with a vowel, typically. But I'm not going to be grading you down for that. It's a little bit nitpicky, but that is generally the case. So what have we looked at so far? Just binary compounds. So this is a little flowchart. Binary compound, yes, it's a binary compound. Next question to ask yourself, is a metal present? Okay, if it's not, if there's no metal present, well, it's type 3, you're going to use prefixes, right? The monos, dis, tris, and tetras. If there is a metal present, you need to ask yourself, does that metal form more than one cation? Generally speaking, asking yourself if it's a transition metal will be easy enough, but there are some exceptions there. Generally speaking, is it a transition metal? If it's no, you're going to type 1. So you're just going to use the element name for that cation. But if yes, if it is a transition metal, if it does form more than one charge, you're going to have to communicate the charge of that metal and use a Roman numeral right after the element's name in that compound name. I'm throwing this flowchart in here just because it mentions polyatomic ions. So if it's a binary compound, if you're saying no, ask yourself, is there a polyatomic ion present? And you realize if there's no here, so it's not binary and there's no polyatomic ion, we're not dealing with it right now. That's a different course. So we're only going to deal with these polyatomic ions. If there's a polyatomic ion present. We're just going to name the compound using our normal procedures for naming a binary ionic compound. So it's not actually that complicated. We're going to finish up with acids here. Acids can be recognized by the oxygen that appears first in the formula. Okay. For example, HCl. This is hydrochloric acid. You guys probably recognize this just by sight because it's used so much in examples. But this is a hydrogen. I can tell it's a hydrogen. This is an acid, and I can tell it's an acid because of that hydrogen in front. There's also a molecule. There are also molecules with one or more hydrogen ions attached to it. How many hydrogens are there isn't that important for identifying whether or not it's an acid. It's just the fact that the hydrogen is in front. Okay, is in front. So if the anion, okay, so I'm not talking about the hydrogens, but whatever the anion is, the thing that follows the hydrogen, if it does not contain oxygen, the acid is going to be named with the prefix hydro and then the suffix ic. For example, we got an anion with no oxygen. Okay, it's just chlorine, or a chloride ion, I should say. And so we're going to have hydro, and instead of chlorine or chloride, the last syllable, we're going to replace the last syllable with ic. So hydrochloric acid. Now this is a polyatomic ion. This is a cyanide. This is cyanide, that CN, that's cyanide. But there's no oxygen in that anion, just the hydrogen. So we're going to go hydrocyanic instead of cyanide, cyanic acid, hydrocyanic acid. And here we have actually two acidic protons, or two acidic hydrogens with an anion where there's no oxygen still. So sulfuric acid, hydrosulfuric acid. Notice I'm not telling you how many hydrogens there are, because the charge present on the anion will tell me that. Sulfur, as an anion, is going to have a -2 charge, so I'm going to need 2 hydrogens to balance that out. Now, if that anion does contain oxygen, okay, there's still going to be the hydrogens in front. That'll never change. But if the anion does contain oxygen, it's known as an oxy acid, okay, an oxy acid. So that suffix ic is added to the root name if the anion ends in ate. For example, if I have HNO3, that is nitrate. NO3 is nitrate. That's a polyatomic ion that you want to memorize. It's nitrate. I'm simply going to replace the ITE with IC. So that becomes nitric acid. H2SO4, that is sulfate, okay, with -2. That's why there are 2 hydrogens in front. That becomes sulfuric acid. And then we have the acetate polyatomic ion, C2H3O2, with the acidic hydrogen out in front. That becomes acetic acid. Again, still thinking about if the anion does contain oxygen, we're going to use the suffix OUS, right? Us, not, we're not using ic anymore, the IC. You're going to use the suffix OUS. You're going to add that to the root name if the anion name ends in ITE. For example, very close to nitric acid is nitrous acid, because that NO2 is nitrite. I'm going to replace the ITE with OUS, so that's nitrous acid. I have sulfurous acid, and I have chlorous acid. That's a chlorate. I'm sorry, that's a chlorite polyatomic ion. I'm sorry, it's a chlorite. Then becomes chloric acid. So again, looking at a flowchart, ask yourself, after you identify that it's an acid by that hydrogen out in front, ask yourself, does the anion contain oxygen? If no, you're simply going to start the name with hydro. You're going to use the root of the anion's name and then add IC instead of the last syllable, and that's your name. If the anion does contain oxygen, you need to check the ending of the anion's name. Does it end in ITE or ATE? If it ends in ITE, you're going to have something us acid. If it ends in ATE, you're going to have something ic acid. Let's finish up with a concept check here. Which of the following compounds is named incorrectly? Now, I'm going to show you the answer, but I want you to generate yours on your own. So come up with your own answer. Press pause if you need to. because here comes the solution. Correct answer is B. The correct answer is B. The charge on that oxygen is a -2. Since there are 2 oxygen atoms, the overall charge is -4. Therefore, the charge on the titanium must be a +4 in order to balance that out, not the +2 that we've indicated here by the Roman numeral. Okay, everything else is going to be A-OK. All right, and that will do it for Chapter 2.